I guess you all can see my screen, and I guess we can start with this webinar. So thanks a lot for everybody for joining us today, and for those who maybe will watch this recording later on our YouTube channels. I'm really proud to have here today one of our two funded initiatives from the Commission, from the European Commission, Pulsate and LAMPAS. And the topic of this webinar will be a laser-based solution for manufacturing, because it's something that basically will help us to build up some synergies with among these two initiatives. So now I change slide. There you go. So here you can see our agenda for today. So we will start with a little bit of a couple of words from myself that I'm already starting to do. And then we will start with the first project of the two. So we decided to start with LAMPAS today. And basically, we will have as a speaker first a representative from TRUMPF, our partner Johanna, that we will talk a bit more about the laser and about the machine that we are building. But about this, I will tell you a couple of words myself as well. And then we will have David Brunel from LASEA that will talk about how we will integrate all the parts of the machine into a final machine that we will have at the end of the project. Then in the second part, we will talk more about Pulsate. That is not an R&D project like the LAMPAS one, is more a service provider, helping for building basically a knowledge and a connection of laser technology also to companies that don't know that yet. And we will have first our coordinator, Pablo Romero from Pulsate coordination, also from AMEN. And also afterwards, we will have one of our partners, we will have Paul Butler-Smith from MTC, talking a bit about the same topic that is also LASEA LAMPAS talking about, that is more laser-based surface structuring. Then we will have a closing words, and then some also networking with you attendees here in the room. So please always free to ask questions after every talk, because we will make a little break after every one of that, and then we will have a bit more of a round the table afterwards. Now, just to give you a couple of words about who we are as EPIC. So we are organizing this event. We are also a partner in both of the two projects, and you see it here. The best way to represent it is this slide, because all these little logos are all associates companies in EPIC. That is the largest photonics industry association in the world, and covers basically all the possible technology where photonics is involved. Just here, a couple of words about it, more in specific. The aim and goal of EPIC is to promote the sustainable development of organizations working in the field of photonics, mostly in Europe, but also with an eye of outside of Europe. So that's very important to have also members and anyway attention and knowledge about what is happening outside of Europe. And of course, we support them in a technological way, but also on a commercial and more marketing side. Then I believe that if you join this meeting, probably you know already what photonics is about, but here I report some of the elements and topics and maybe the products that our members produce or integrate. So for example, lasers for many applications, but also lighting system, optics and optical components with fibers, detectors, photonics integrated circuit. That is also something very useful for many applications, and so on. So photonics is really everywhere. And then basically here, the little heads that are below, they're always getting smaller because we are growing as a team. At the moment, we are 15 people working for all the members, and also for all the activity that EPIC is really interested in, also application of photonics. And on the last point, you can see a bit of the activities that we do. For example, we publish market and technology reports, even done by ourselves, not only the commercial ones. We organize technology workshop like we try to do here, also a bit engaging with people, engaging with the possible, talking about the challenges that the photonics can face and how to help each other and to face it, and also to build collaboration and business. We participate in EU funding proposals, as you might imagine. Here we are also partners in these two initiatives, and you find also all our activities in our website that is reported here. So if you are interested in knowing more about EPIC, that is the place to go. And also you can ask me as well, of course. Now, I will just make a brief introduction of the two projects. So LAMPAS is the first one, is all about surface enhancement that is inspired by nature. So basically, it's known that controlling basically the surface characteristics at a nanoscopic level, a micro nanoscopic level, you can basically obtain basically induce some special functionalities to the surface, and that could be, for example, antibacterial, self-cleaning properties, friction reduction, and all these activities are really important because we could apply them to certain surfaces in our real world without using special coatings or something that is more not really environmental friendly. And this capability is really connected to some specific technology that you will hear, especially today. So you need special lasers, you need special scanners, special also monitoring system to obtain this, and of course also a final machine for this. And the important thing to make this really appealing for the industry is that it has to be able to fit the mass production and to be really low cost and also high throughput. In this case, here you see some examples of natural surfaces, but what we really are building here is what I already mentioned so far. We will need really, it's a system that we are building in LAMPAS that is based on this multi-beam processing, where we have first the high resolution multi-beam processing, then there is need of this deflection system for these beams, then there is an ultra-short-pulsed laser ablation for ablation needed, that, and you will hear a bit more about it very soon from Johanna. And then we will need an inline monitoring system that we have actually composed of two parts in LAMPAS. And then we have, of course, demonstration and validation with the simulation that is always working in parallel, but the final machine as well. So it's really nice that we have today here Lasea explaining how they will then integrate all these parts to build a final machine. Here are all the project's partners involved. Some of them I already told you. Our end user and early adopter is Bosch, is BSH, sorry. Bosch is more providing in self-simulation. And these are all the partners also involved, and you are very welcome to visit also our website and our social media that you see here. Then jumping to this next project, we are talking also today about Pulsate in the second part of the project. This is more like a network based really to bring closer to all small and medium enterprises laser-based advanced and additive manufacturing. With this, what does that mean? So basically, this is a bit the scheme. So this picture that you see here is what really helps us to understand a bit what we are doing. So we are promoting in these 4 years of the project and facilitate the adoption of laser-based advanced and additive manufacturing by SMEs and also a bit larger companies. But also we have different ways to do this. So we have some services and even cascade funding. So if you see here, we can really give money to you. So, and to little consortia that you can build in two kinds of open call. There are technology transfer experiments and adopter user cases. But then we have also a way to provide you with a lot of different services. So infrastructure, really, we have 6 competence centers, really being experts in all possible technology when laser is involved that is useful for manufacturing, software services, also more business part, digital maturity assessment, also digitalization is really important for in advanced manufacturing activity. And so we have also experts in this. Courses and trainings will be available soon, and also technical strategy and matchmaking meetings, so that the things that keep also the community to grow. For this, just I mentioned the technology, the next open calls. So the next open call for technology transfer will be starting in May, so second quarter of 2022, while the adopter user case will start really beginning of next year. So if you are interested in a feasibility assessment, for example, or also implementation, always connected to laser-based advanced and additive manufacturing technologies, you can think about it. We will give you some money for a few months, and we will support you in this way. For the technology transfer more is a bit more, is a longer project. It has to be with a small consortium, and he is providing even 150,000 euros for a 13-month project. And so if you are more interested in hearing this, you can check also on our website. These are our companies that are building the 6 competence centers, and also some other companies building a bit helping in building this new community, this network that is not new, but it has to be definitely to become stronger and also broader. And here is more like our social media part, where you can hear a bit more about what we are doing, what we are about to provide also services. We are a bit young, so we are still at the second year, but we are now really bringing in place all the activities that we are planning to do for supporting laser-based technology in Europe. And with this, I would say, let's go back to the agenda. Let's not talk too much just by myself. So it's a pleasure for me now to introduce you to Johanna Dominik from TRUMPF, and she will introduce a bit what their super powerful laser is doing for LAMPAS, and then later on we will continue with the other partner for the integration. There you go, Johanna, the floor is yours.
Thank you, Francesca. I will just share my screen. So you should be able to see my screen now. Again, thank you, Francesca, for inviting me and for the opportunity to be a speaker today. My name is Johanna Dominik. I work in R&D at TRUMPF. Especially I work with the disc laser amplifier that I'm going to talk about today also, but the topic of my talk is a bit more general. It's about high power ultra short pulse lasers for industry. So let me start with showing a few examples of applications. So this is not a comprehensive list, just some examples. One is transparent materials processing, such as glass cutting and glass marking, which can reach higher processing speeds with higher power lasers. And also some applications like the cleaving of thick glass becomes possible only with higher pulse energy, for example. Then there is the surface structuring, which is, of course, very important use case because it's what we do in LAMPAS. Francesca just showed you pictures of biological surface structures. And here I have from a paper pictures of laser-made periodic surface structures that can be created with an ultra-short-pulsed lasers. And in LAMPAS, the idea is to create these functionalized surfaces with high throughput, which is possible with a high-power ultra-short-pulse laser. Then there are other applications that become possible with high pulse energies, such as secondary sources like extreme ultraviolet generation, X-ray sources, or particle acceleration. And also one application that has been in the news a bit is the laser lightning rod, which is also a publicly funded project. And here you can see a picture of the top of Mount Sentis in Switzerland. And a TRUMPF laser is in this building down here and is creating a filament in the air, which acts as a lightning rod. So this is also a very exciting new application. Now a little bit about our company. So TRUMPF is a family company based in southern Germany, but has worldwide presence with over 70 locations in all over Europe, America, and Asia. We have two business divisions. One is machine tools for sheet metal processing, and the second is laser technology. So I'm going to talk today about laser technology. We have a lot of different laser technologies. As you can see here in our portfolio, we have CO2 lasers, disc lasers, thin disc lasers, which is also what the technology that I work with diode lasers, fiber lasers, pulse solid state lasers, which is actually a rod laser, and we have ultrafast lasers, which are also the topic today, and marking lasers. So if we look at the true micro lasers, the ultrafast lasers, we have already wide range of possible parameters. So the smallest one is the TRUMPF 2000, which is a fiber laser with up to 100 watts power. There's the TRUMPF 5000, which has a thin disk regenerative amplifier and produces up to 150 watts output power. And the newest ultrafast laser product is the TRUMPF 6000, which has the InnoSlab module from LAMPAS, which is a TRUMPF subsidiary, as its main amplifier with up to 350 watts in the infrared. So as you can see already, we are going into higher average powers here, and all of these ultrafast lasers are possible, are ytterbium infrared lasers, but they can also be converted to the green and UV. And then we have nanosecond lasers, which are cavity damped disk lasers, which go to higher power levels, up to 2 kilowatts in the IR. And we have processing optics, and also, for example, LLKU is the hollow core fiber as a transport fiber, which is also very interesting technology for another day, maybe. And here are also some more examples of applications for these lasers. Now, let me talk about the thin disk technology, because we want to go to, so what I personally do is I am involved in the development of thin disk amplifier for ultrafast lasers, and for this we use the TrueDisk technology from the continuous wave thin disk laser. And here is a picture of state of the art thin disk laser, which produces up to 12 kilowatts average power with here an M square of about 10 from a single disk. So this is a technology that is really well suited to create really high powers, and we use a lot of these components for our amplifier as well. This is this pump unit. This here is the pump unit with the pump diodes here. The thin disk is about here, and the black box is the pump optics that bring the pump light to the thin disk. And then here's a resonator, which has an end mirror here. There's a folding mirror. The thin disk acts as an active mirror, and here's the output coupler. Now we want to use this thin disk to amplify an ultra-short-pulsed laser, and in principle this is really easy. So we reflect the seed laser from the thin disk, and it becomes amplified. But in a single reflection, the amplification factor is not really high. It's typically between 10 and 15%. So what we do is we use a mirror array to bring the beam back toward the same disk several times to get a higher amplification factor. Here on the left, this is the thin disk inside the pump cavity, the pump optics, and here is a picture of the mechanical construction of the multipass amplifier with me standing next to it. And as you can see, we have put it into a really stable mechanical construction, so it is ultra reliable in an industrial environment. For the mirror array, it is also important that the individual mirrors can't get misaligned because of the long beam path inside this amplifier. This is a challenge, and for this reason we have developed at TRUMPF a glass welding process for the mirror array. So we use a TRUMPF 2000 laser and the top weld optics to weld the mirrors onto the base plate, and this way there are no mirror holders that can get thermally misaligned or otherwise misaligned. Move on. Now we want to apply this amplifier to the LAMPAS project, and Francesca already said a few words about the project. So What we are doing is we use an ultrafast laser to do a direct laser interference patterning process. Here are the project partners of this project. We have a DLIP module, which includes splitting the beam at a diffractive optical element into two beams that can later interfere on the workpiece. We're going to have a polygon scanner as a fast scanner optic to get the high throughput, and we're going to have process monitoring, which is obviously really important when you're developing a new process and to get reliable process results. And for the LAMPAS laser, we have a first laboratory setup, and the way we have designed this laser is to use a TRUMPF 6000 as a seed laser, which consists of a fiber oscillator and stretcher, a preamplifier, the InnoSlab amplifier, as I have mentioned, modulator, in this case an AOM, and a compressor. We have an isolator to protect the TRUMPF, and we go into the multipass amplifier. We have 18 disc reflections, then an end mirror, another 18 disc reflections, and we rotate the polarization with a wave plate and couple out at a thin film polarizer. And then not part of this picture yet, but part of the LAMPAS laser will be another modulator that will communicate with the scanner, active power stabilization, and another compressor. So we are going into the multipass amplifier with pre-compressed pulses and then do a second compression stage. And here's a photograph of a first lab setup of this laser in my lab. Now I have first results from this lab experiment, and so we have a TRUMPF 6000 as a seed laser with 285 watts output power, a repetition rate of 375 kilohertz, and the pulses are pre-compressed to 8.5 picoseconds, and a pulse energy of 0.76 millijoules. And here is the output power and M square as a function of the pump power of the multipass amplifier. And you can see the output power goes up to about 2.3 kilowatts. So this is very good news for us because our LAMPAS working point is much lower than that. It's slightly above 1.5 kilowatts because we're going to have some losses at the modulator later. So we have here about 1.6 kilowatts at our working point. Pulse energy slightly above 4 millijoules and an M square of about 1.3. And the beam profile, especially in the focus, is quite round and is well suited for the process. Let me summarize my talk. High power and high pulse energy ultra-short-pulsed lasers will enable higher productivity for established applications such as transparent materials processing and laser ablation. New beam sources with high pulse energy and high average power enable new applications such as secondary sources and geoengineering. Then something that's very important to us is that the beam sources are industrially stable and reliable, which they need to be in order to be successful in industry. And the LAMPAS project is for us really a great project because it enables us to get a kilowatt class ultra-short pulse laser integrated into a machine with an industry-ready use case in surface functionalization. So yes, thank you for your attention.
Thanks a lot, Johanna. Thanks a lot for the great presentation. And so, as I told you already, to all the audience also in the chat, please, you can use the chat. You can raise your virtual hand. Please do anything you want to just attract my attention. So at the moment, maybe we can unshare your screen. So like this, yeah. So we are back in the room for those who are there. And so Johanna, so if the people are still a bit shy because they have still to warm up, I have a question. So I've seen that, we have also later a question. I see now they're all getting. But first I ask you my question. So now we are basically at the stage that you, if I remember correctly, you are almost about to deliver the laser to LASEA for integration. Is it correct?
It is correct. We have to do some final assembly. As you saw on the picture, the laser is still on a breadboard. It's not in the final laser head, so we have to put it into the final laser head. Yeah. Okay,
perfect. Yeah, but then basically we can say for your stage of the work, you are almost at the end. You can basically look a bit back and look at what were the challenges. So because, you know, at EPIC, we always like to find the challenges, what was solved, what was really, that was not letting you sleeping at night. So maybe you can mention one thing that you thought it could have been, solved easier, but then it was really a challenge, or something just technical that you know it was a challenge before already, because 1.5 kilowatts at these few picosecond pulses for sure is not, it was not to underestimate. But if you have an example of a challenge that you said, then we had to struggle a bit, but we managed, what would it be?
Let me think. So we have, during the course of this project, we realized that we need to look at the quality of our optics, and we had to really test again our optics. So not just use the same again, but really check for the high pulse energy and the high average power, which optics we choose. So that
okay, so that was a bit damage threshold and compatibility exactly with the optics. Okay, and did you have some suppliers to talk to, or it was internally solved?
A bit of both.
Both. Okay. Yeah. Makes sense. Then it was like you asked for a bit of help, but of course you have your own expertise, and very good. So now we have a question from Jeremy from Sinova. So please, we like to, you wrote it because then I know what you want to tell, but we like you to unmute yourself and you ask yourself the question, so makes it a bit more lively.
I can unmute myself.
Yeah, very good. Thank you. Thank you for joining us. Please, Jeremy, ask your question.
Well, thank you for the presentation. It's really impressive, actually. Very good work. And the mirror array actually looks beautiful. So, you know, beauty in the technical execution. My question is regarding the 12 kilowatt CW output, which is quite impressive. Are you looking into converting this to green down the line at some point? Because at the moment, TRUMPF only has, I think, 2 kilowatts maximum green, right? So how are you looking into that?
That's a very good question. Actually, I'm sorry, I can't answer it because it's not my my area. So I'm sorry, I don't know what is planned with the green continuous wave lasers.
Yeah, at least.
Maybe, Jeremy, you can tell us a bit about Sinova and why are you attending this meeting? So it's nice always to understand a bit who is joining us. So for those who don't know what Sinova is doing.
It's simple. We're a small Swiss SME, and we focus on building machining platforms, so 3 to 5 axis. And the core of our technology is the water jet guided laser. So we use a water jet as the light guide for the laser, and that's why we're interested in the green wavelength, because it has low absorption or high transmission in the green with water, and that's what we want. So that's what we do.
Yeah, I believe if we want to talk more about the green, maybe we can find some colleague of Johanna that would like to talk to you in private. This is what also EPIC is doing. So don't lose your your trust. You will get to know this information, and we will maybe reach out later to you. Okay.
Yeah, sure.
Very good. Yeah, sorry.
Yeah, of course, you can reach out to me via LinkedIn or write me an email, and I can ask around or forward it to the
very good.
person.
That's what we want to hear. Thank you, Anna. Then we have also a question from Paul. Thanks a lot, Paul, for joining us today from MTC. You can ask your question.
Thanks very much, Francesca. Johanna, thanks very much for your presentation. I was really curious when you were presenting your architecture using DLAP structure. So the question really is that integrated into one of your existing sources, or is it a kind of standalone setup, a dedicated setup, if you like, for only DLAP type processing?
The DLAP module will be integrated into the machine, and which I think will be presented in the next talk. So we don't have it in our lab. We only build the laser.
Okay.
Yeah, maybe Paul, for this, exactly. We have here Johanna providing the laser, but David now, that maybe is the time, let's do like this. It's the best way, it was the best question to ask now, because he presents the floor to David Brunel from LASEA, that is integrated not only Johanna's laser, but all the devices that we are preparing for the LAMPAS project. And so he will maybe have a couple of words for you in this talk, or maybe afterwards if the questions are not answered. Let's keep this, there's some details more for after David's talk. So please, David, if you want to share your screen, the floor is yours.
Thank you. Okay. Do you see it?
Yes, also in full screen mode. The floor is yours.
Thank you very much. So good afternoon, everyone. I'm going to talk here about the machine, as we just discussed, which is developed inside the LAMPAS project. So the objectives are in the project in terms of machines is to have a development of a very high power ultra-fast laser macro-machining system. So here we are talking about the system itself, with a goal of to be able to texture very fast, very quickly large surfaces with multi-scale patterns in terms of speed. So we are talking of an objective to reach at least 1 square meter per minute. And for areas, large areas texturing, by large, we mean more than 300 square millimeter. And we expect to reach up to 600 square millimeter. So first of all, just summarize about the high power laser processing paradigm. So when using high power, we have two scenarios possible. So the first one being a low pulse energy and high repetition rate, and the second one being high pulse energy and moderate repetition rate. In any case, one issue that could happen when we use high power lasers is to have heat accumulation. And so for that, one solution is to combine different technologies, especially here. So as already said, we are going to combine the DLIP, so in order to provide interferences on the workpiece, and that will be combined with a high-speed polygonal head. So we'll have at the same time the speed and the interference being made inside a large spot area. So we can have structures smaller than the spot size itself. And this will be combined as well with high power already presented by TRUMPF, and also an inline monitoring developed by the partner NIT that will look inline the ablation. So this is an overview of the final machine, which is currently being built. So that will combine different components: the 1.5 kilowatt picosecond laser, the high-speed interfering beam delivery system, and the inline monitoring system. So here we can see the choice was made to integrate it as close as possible to an industrial machine, where the laser will be located underneath the texturing area, as you can see here on the picture on the right. Here we are talking about a laser of several hundred of kilo and with a footprint of 1.2 meter by 2.5 meters. So this is a scale above the current standards of lasers. And also it will be underneath a large surface granite. The idea to have a very compact design. So this is another view. So this is the draw of the laser. So it will have very easy access. It will be very easily possible to pull the laser out of the machine for maintenance on site. We will also integrate the high-speed multi-scale DLIP and combination of a DLIP with the polygonal head. So here we are talking of a polygonal head with a working distance of about 280 millimeters that will produce interferences on the workpiece. So the DLIP system is located in the top box, the box on the top of the full assembly that you can see here. And this full assembly will be combined with translation stages. There is one on the gantry and one on the granite on the bottom. Those stages have a travel length of about 1.5 meters. So this is really dedicated for large surface area. Another integration is about the inline monitoring system, which will at the same time be able to do some analyzing, so infrared with an infrared camera of the ablation occurring in real time. And once the texturing is done, so as here we are talking about multi-scale structures, there will be a FFT system which is that will analyze the pattern after the machining in order to have a feedback on the quality of the machining itself. And so in order to manage this high power beam laser, so we will integrate a beam stabilization system. Why that? It's because when using high average power with short pulse or not, we will have some heat produced, we will heat the air itself, and this can generate some beam jitter, in general a few tenths of hertz, that can, with the distance, so that will be like an angle, and with the distance that will be amplified by the distance. As here we are talking of very large distance, so such systems is really mandatory. It is composed of 2 accurate positioning mirrors, motorized mirrors, and 2 beam positioning sensors with a wide intensity dynamic range detector of more than 1,000, meaning that the same system can be used with 1 watt and up to 1,000 watts. So the positioning of those mirrors and the sensors are located at specific locations on the beam path of the machine. Also, something else that was taken into account in the machine is the optical beam path itself. As we are talking about very high power, we need to avoid to have any transmittive optics in order to avoid nonlinear effects like phase shifting, for example. And so here on the machine, we have only 2 windows where the beam will go through. That was a specific design for the machine. And also all the mirrors are obviously high reflectivity mirrors with a reflectivity solved to be more than 99.9%, but in reality it's even more than that according to the measurements. Also another point here regarding the optical boxes, they are all assembled in a class 5 white room environment in order to avoid any dust. We decided to not go for an overpressure air inside the box in order to avoid any airflow that could make the dust fly around. So here are some preliminary results. So those results were obtained with a standard galvo scanner. So not yet with a polygonal head. So far the speeds are quite short so far, but in any case we can see that we get very nice results of the pattern itself. So here we can see some structures with a period of about 8 microns and a height of about a bit less than 1 micron on silicon. We also have very nice structures on steel as well, which was 1.4 steel with an average depth of 0.6 micron. So here are some other examples and measurements done of hydrophobicity of the results. And we can see that thanks to the structure, we could get contact angle up to 140 degrees, and this on the full surface of the pattern. And we also observed some very nice diffraction effect on the surface that were machined. This is due to the combination of two patterns at the same time. So we have the micro pattern, which is generated by the interference themselves. And on the top of it, and they are generated by the interaction of the laser with the matter itself, we also have lips, and we can control the orientation of the lips in regards to the pattern, to the interfering pattern. So we have quite a good control, and we can, thanks to that, we can enhance the diffraction effect. In terms of efficiency, so far, again with the standard Galvo, we could reach, we could texture 150 square millimeter in only 15 seconds. And the objective of the project will be to reach more than 1 square meter, again, 1 square meter per minute, thanks to the polygonal head. This is a short example. So to conclude, so here in this project, so we are going to have very high performance requirements machine integrating a 1.5 kilowatt laser, picosecond laser, with the first demonstration of interferences patterning system, a DLIP, combined with a polygonal head, and this for fast beam delivery. At the same time, we have on the same machine an inline measurement system in order to analyze the quality of the machining itself, and also the heat generated during ablation. And to finish, so we'll have a machine that will be of very high performance processing, that will provide very high performance processing with a goal of 1 square meter per minute, and it is expected to reach up to 2.5 square meter per minute. So this is to conclude, this is a very perfect tool for surface functionalization application in order to reach industrial scale. So this is a part of the development of a new generation of products in terms of machine with novel functionalities, including anti-fingerprint surfaces, decorative holographic motifs, are also easy to clean and bacterial properties. We expect a performance improvement of products of more than 20% and accelerated product development after the project. So we expect to have a strengthened global position of European manufacturing industry. And thank you for your attention.
Thanks a lot, David. Thanks a lot. So now we had a bit of an overview. Now from the guy that has to put all the pieces together is David for us. So I don't know, Paul, is now all clear? Or you want to maybe ask another question to David to get maybe a bit more into details?
Thanks for giving me the opportunity. No, I think the presentation covered really what I was about to ask. So I was just curious to see the sort of application side of the laser, as I was asking the question earlier, rather about the whether it was integrated into the source or it was a sort of standalone system. So this kind of described, I think, the system setup and its capabilities. So it pretty much answered my question, but thanks all the same.
Perfect. Yeah, then maybe a couple of words about you, Paul, because you will speak later, but maybe it's now the good opportunity to tell what is your interest. So MTC is one of our partners in Pulsate as a competence center, but maybe you can talk about a bit your competencies in MTC.
Okay, that's
first.
absolutely fine. Well, I'm sure a number of you have heard of the MTC. We have a number of different sources of lasers for mainly looking at research and industrial applications, where we look at development of processes for various laser systems. So we have a wide range from the Sonova system, which we heard about earlier, to some of the TRUMPF systems, or the systems built around TRUMPF lasers, and also some of the ultra short. Me personally, my background is materials, and I'm really interested in the laser processing of different materials, more so the more difficult to process materials. I did my PhD in diamond materials, which initially was really interesting, and now developed into quite a big application area. So that's MTC and myself as a background. But today we're going to talk about some of the applications in tribology, which I'll talk to you about a bit later.
Very good. Thanks a lot for the introduction, Paul, of yourself,
Okay,
and then to tease a bit the audience for waiting until your turn. So now we have two questions in the chat. So one, I will read it because I see that Alain is in an office, he cannot talk, otherwise he disturbs his colleagues. But let's start with Kiran. Kiran, can you maybe instead switch on your microphone and ask the question yourself? Let's see, Kiran 1. Kiran 2, Kiran 3. Otherwise, I can ask the question. I have it here. So the question is, what is the maximum temperature rise due to heat accumulation that you have, David, I assume in your test, that was probably the referred to.
So we did a bit of work on the simulation itself in the project LAMPAS. With Bosch, actually, we work together on this, and such temperature we depends on the parameters, obviously, but don't remember exactly the maximum, but it's about several hundreds of degrees at least. I've got in mind more than 700 degrees, but it can be even more probably, but I don't remember the maximum. But this is in this range, and we are trying. Actually, the goal of the simulations is to make a link between the temperature, the measurement of the temperature, and the simulation as well with the quality of the surface. And the goal being to have a very good control of the process parameters to reach the performance in terms of speed, but also in terms of quality.
Very good. I guess hopefully Kiran is happy with the answer. Otherwise, please comment back. So now I go to the question of Alain. That is actually not able to speak. So I ask his questions. He congratulates for the talk. And he also asks, basically the machine is composed by two parts. One is more laser structuring and the other one is for measurement. Now he would like to know a bit more about the measurement equipment that we are using. So it's not LASEA's main tool, but he knows what he will integrate. So David, please, maybe a couple of words about our measurement and monitoring systems.
Okay. So I don't know all the details, but what we are going to integrate is two components. The first one is a camera, an infrared camera, in order to measure or to make a correlation between the measurement of the camera and the temperature of the surface itself, this in real time. And the second component, it's a FFT, so a fast Fourier transform system that will, after the machining, so the structures will be positioned just underneath this system, and it will make a Fourier transform analysis in order to reconstruct the surface pattern.
Okay, so hopefully this is enough. And of course, as just to mention, the people responsible for these two systems are not here today, but they are our partners. So if you want to know more, we can, of course, introduce you to our partners doing more the measurements. So TU Dresden and NIT mostly, and they can for sure come back to you with more details. And then there is another David in the room, surprise, surprise. And he has a question for David as well. And he's asking, does the interference pattern remains when deep engraving is performed? When he says, for example, higher than 100 micrometer depth. And he cannot talk, so that's why I talk for the other David.
So far, we did a bit of investigation regarding the depth, but this is not our main target so far. The deepest we could reach was a few microns. From memory, it was about 6 or 7 microns. But that's something, I don't think this is possible to reach 100 microns of depth with such system that we will have on the machine. Again, our main goal is to have a multi-scale. We expect to have dimensions in the range of about 10 microns, between 5 and 10 microns in terms of wide, and about a few microns in terms of depth. This is the main goal. We have on the top of this some lips.
Okay, good. I guess also if David has some comment further, he can write it again. Otherwise, we give the floor again to Jeremy because he raised his hand and he can speak. So it's very good.
Right. Very nice presentation. Thank you very much. A quick question, specifically, I think going back to the heat accumulation, when you're trying to look at contact angle and super hydrophobicity, surface chemistry plays a huge role, and I wanted to know a little bit how you were dealing with the aspect of the surface chemistry on top of the surface texture.
So on our side, we have not investigated the chemistry. We, at least at LASEA, we have mainly our ways of measurement are mainly focused to topography. And the quality, so the quality indeed, the heat induced some change of the chemical structures and also of the structures itself, but we have other way of qualifying the quality, which is more related to burrs, for example, or some observation to the melted. But all this development related to the heat and the quality is more done by another partner, which is NIT and also Dresden at the same time.
Thank you.
Also, we can connect you for more details. Yeah, then Ralph from Finisar. Welcome. Thank you for joining us today. Please, you can ask your question.
Yeah, thanks very much. Thanks very much for setting up the session. That's great. And also thanks very much for the previous talks. Very interesting. I have a question about the heat dissipation, and there are a number of approaches to avoid that. And so what I would wonder is, one typical approach is to use athermal ablation by using really short pulses. And could that be a solution here? Has that been considered? So that's in the range of femtosecond pulses. David, maybe you want to comment?
Yeah.
Yes.
Yeah. He was unmuting himself. I guess there was some trouble. Please, David.
So actually, yeah, indeed, that's true that we often hear that femtosecond is a cold ablation, but this is not right. We always have residual heat inside the material. I think this is quite well known now. And in order to avoid the quality, we are working on this. So we are working on simulations to do that. And we have developed a simulation model that can predict the temperatures that will be reached by the material. And according to other parameters, like the speed, for example, we can know in advance if the quality will be good or not after the machining. I hope this replies your questions.
Okay. So you say that you can accept a certain temperature change of your sample?
Yes, during the machining anyway, you will have an increase of the temperature, but there is always a critical temperature where the structure of the matter will change, and this is actually a saturation of the material itself. If the temperature cannot get away fast enough, then this is where the bad quality appears. And that change, this is why every material have a different critical temperature.
Okay, thanks very much.
Perfect. Then I guess we are, of course, out of any agenda of any time, but good that we have some buffer for discussion. It's nice to have them after every talk. So it's good that we can maybe postpone the next talks, but we had already a lot of discussion. So that's thanks a lot for all of you participating. And thanks a lot for our two speakers from LAMPAS again. So Johanna and David, thanks a lot. Please now stay tuned because now we get your round, but we have also now from Eamon and from MTC, as you heard already at least about Paul. We have some expertise on surface structuring, of course, also in our competence centers in Pulsate. So it's my pleasure now to give the floor to our coordinator, but in this case also expert in surface structure in Pablo Romero from Eamon. Thanks a lot, Pablo, for being here, and the floor is yours. You're muted. Just to optimize the time. We are getting your screen soon. Yes, we see it.
Yes, okay.
And we also hear
again,
you. Very good.
Again, muted, yes. Thank you very much, Francesca. And yes, I'm Pablo Romero from IMAN, as was already presented, and would like to thank the organization of this session, of course, and not only similar but friend and colleagues from LAMPAS that it's very nice to join. The last few questions that were raised were interested because it all can be summarized in, it's complicated, let's say. The laser-based manufacturing all sum up in just focusing a laser in an area and make it work, but making work is interacting with the material. And I like to always show this triangle. Can you see my full screen? Because I have some.
Yeah, yes.
Okay.
We went in full screen and all good.
Oh, great. We have this interaction between material, wavelength, or characteristics of the laser and the parameters of the laser. Dictating the optical interaction and dictating also the material behavior, which is the optical behavior, but also the physical and chemical behavior. So you were all very, very good and very precise in pointing out heat accumulation, the chemistry, and many more things. Actually, just by changing a few things here, which is the wavelength that was also mentioned. I'm interested in green, I'm interested in infrared, but there are many range of laser parameters, the interaction time, and the precise distribution of the laser on the workpiece, and how it is used by the workpiece, meaning the thickness and the strategy of patterning the workpiece with the laser. You get a number of effects, different effects, which in combination with how you distribute it in time, it gives rise to a number of processes. All laser processes are basically the same, but are hugely different in the results in the materials. So at the end, the knowledge of the optical interaction and physical and chemical interaction, having a very deep knowledge of that is critical to design the process. And design the process must be before deciding on which laser and which equipment you need, because all the everything around the equipment selection must be subdued to the design of the process. So all this interaction matrix. And what's special about laser-based micro machining and texturing? Well, quite a lot of things. First of all, why it's interesting, why we get into this mess, into this complication. It's because, of course, surface is the only interface between a body and the environment, and there is where happens all exchanges, thermal exchanges, fluid dynamics, heat, and wetting, and everything. The learning about how the surfaces that are optimal for a certain process work, let us know that normally surfaces are designed by their physics and their chemistry, but are normally not a single roughness that is optimal. It's a combination of several hierarchical structures, which are quite difficult to produce. and different uses require different density of structures, but normally 50% density of tenths of microns combined with a few micron to sub-micron structures is something that works perfectly for both fluid dynamics and for wettability, for instance, super hydrophobicity, self-cleaning surfaces, lots of applications that are interesting. To go so precise in both topography and chemistry, we need to get use of precise process design also at a few picosecond level or even femtosecond level, depending on what you need. It's not just about reducing the thermal effect on the material. It's about controlling what the material does with the radiation that is absorbed, and what is the precise interaction between the electrons, which are the only ones that absorb in the first place the electromagnetic radiation, with the rest of the structure of the material. So that's why it's not just about heat accumulation, but that's an important point. That's why we go to short and ultra short pulses, but to control the generation of plasma, to control the transport of the heat to the lattice of the material. And also that's why, because we want to go beyond the standard effects of ablation of laser machining and generate some even quantum mechanical effects on the material and sub-micron structures and sub-wavelength structures even. That's why we go for precise beam shaping and beam manipulation, like interference, that is the main point of LAMPAS, but also special beam distribution, multi-beam and flat top hat and ring style and so on. So the question is, with right manipulation of time of interaction and distribution, we can get extreme effects like these a few hundreds of nanometers structures, or very high aspect ratio structures that are in the knowledge of our competence centers because of different research activities like these ones, matching nanometers, different projects, LAMPAS, of course. But the question is, they are not common use in industry. So we have the typical problem of lasers in industry is they have the always present promise of quality, productivity, flexibility. Is easy to set up. You just put a laser and it works. And the barriers of, okay, setting up a process is not so easy. You need to know a lot of things. The awareness in the case of SMEs is especially difficult. I don't know about successful implementations in my case, in my needs. Setting up in the workshop is difficult. It's expensive to test, especially for if you don't know exactly the equipment you need. That's why I mean, first design the process, then decide about the equipment. And there's a number of complexities in surface modification in particular. All the ones that I will not repeat that were mentioned before, about the chemistry, about the structures and so on, but also the lack of standards and some difficulties depending related with quality specifications and quality control and so on. So there's a number of peculiarities in surface modifications. Okay. So, and as fast as I can, I will talk about Pulsate because we are dealing with those difficulties. We are trying to get industry into the benefits of laser-based manufacturing by covering the technology, which is important, but also the competence and business part. So the training and the standards and certification and knowledge part, and the market and finance part, but also, as I'm mentioning, awareness, so they know what is possible in their case and what is available in the market for them. So our project is built on on 3 phases. We just finished the first phase, sorry, of setting up of our operational capability, and we are initiating now our operational support to industries. And we do it through a network, so linking providers of knowledge, providers of technology, demanders of applications, SMEs, which are potential or actual implementers of laser technology, and linking them all together in several ways, mainly by providing direct services, but also during the project by making complete experiments of implementing the technology in a particular case and scenarios. We are these people here, so some of the top research centers with some relation with lasers in Europe. I'm in TRUMPF in Norway, CEA in France, Fraunhofer IWS in Germany, FTMC in Lithuania, and the Manufacturing Technology Center in UK, supported by funding box EPIC, of course, and Glasgow in the digital business and networking, particularly in photonics. And we provide a number of I will not have time to detail, so go to our website and check with us and get in contact with us, a vast number of services. And particularly, as I mentioned, the test before invest and test in our centers services with cascade funding. And we are starting now 10 experiments giving support to 21 or 22, 20 something SMEs in Europe in different areas of laser technology, on real-time inspection, additive manufacturing, digital beam shaping, and surface technologies. So that's why we are strong in that area. Right now, to a number of more than 20 companies in Europe, with a vast number of technologies being tested. And on parallel with that, we are making our own experiments. For instance, experiments on additive manufacturing with real-time metrology and a number of technologies being tested, but one in particular on laser surface manufacturing. So first we checked what was possible with the capabilities of the different partners. You know what is possible in Fraunhofer because it's linked to what is being done in LAMPAS. Actually, it's very much linked with what's developed in Dresden, so with interference patterning and this type of structures, large area, very fast for super hydrophobicity. What's possible in FTMC with direct machining with Picos and Gold lasers, and it's excellent structures for riblet type for self-cleaning, anti-icing. And what's possible in MTC, which will be detailed later on, with also micro machining in GF machine for super hydrophobic surfaces and better sliding and tribology. And we develop in particular a process for a real part, propeller for maritime, where we used a number of digital technologies for simulating the part and detecting the parts, the areas which needed texturing for avoiding cavitation, and developed a process, a quite high-speed process I will show you here, to provide high aspect ratio structures, 1:1, so it's 100 microns thick, the structures 100 microns high, and higher than 1 square centimeter per minute, with all industrial equipment, industrial laser and robot to result in this kind of structures. So in less than 4 minutes, providing full texturing to a real part. So that was our experiment, just to showcase our capability in structuring, which covers only a tiny part of what we offer, but we thought it could be attractive to this audience today. And I'm open for questions or comments, of course. Thank you very much.
Thanks a lot, Pablo. Thanks a lot for introducing a bit, the expertise towards the surface structuring, but also a bit what Pulsate can do for the audience. So now, do we have questions? Because otherwise I have an exercise for Pablo. That he would love it.
Okay.
So let's say we are here and we have these companies in the room, and they are all potential. And maybe, I mean, if you're not too rich, let's tell you, if you are a big company, maybe Pulsate cannot offer you, you're not the real target of our aims. So more SMEs and mid caps. So for the definition of the commission, middle size, let's say, is the maximum. But let's say anybody who is here now and who will listen to the oops, sorry for this, to the webinar later. If you are an SME that is now interested in all this surface structuring, I mean, look, it's amazing what we showed so far. What can Pulsate do for this company that maybe send us an email or one day will access the Digital Agora as an interested person? What can actually Pulsate provide for them?
Yes, immediately we can provide the access to open calls to do one of two things. One is just evaluation of the economic and technical, we call it techno-economic, feasibility of introducing laser in your particular application. So you have an application that you do some other way, or you're interested in surface texturing and you don't know if laser can be used. We do this work for you, and also on top of that, we provide 50,000 euros of funding for your own studies in your company, for complementing our techno-economic feasibility study. At the end, you will have a dossier of the feasibility of the implementation in your case. And we have a methodology for that. And then it's already proven in our first test cases. We will open early next year a call for that kind of studies, okay? And we will offer support to 20 SMEs for that kind of a study. So please contact us if you are interested, and we will tell you how. The second is, okay, you want to go further and you want to test in your particular application, not just make a feasibility study, but a real test. First, we can offer that as a service, and supported by the European Commission, so at very low cost, but it will have a certain cost. But it can be immediate. You contact us and you ask for access to our infrastructures, and we will set it up. Or you can ask for financial support and make a combination of test in our infrastructures and test in your own infrastructures, in your own factory or with your own material. And we will link you to a technology provider who can provide technology to you to cover your needs. And on top of that, support you financially also with European funds. Those will kind of activities will open later in next year, in spring next year, and are, I think, extremely interesting for different companies that are wondering what can they do with lasers, and are a step beyond of just feasibility study.
Perfect. I guess the exercise went very well, Pablo. So
you.
that was
maybe a bit long.
No. It went very well, because now we know a bit also for a simple example. Usually, sometimes when you do a list of services and things that we provide is not always clear. But now, if you do an example based on what we are just talking about, is probably the best way. So now, if anybody in the room has questions, that is not like where do I sign up for the open call, because this we can do also offline. If you have other questions that maybe were not clear, or for some specific application that you have in mind, today, of course, we talk about surface structuring, but we have this Sales Competence Center, so additive and advanced manufacturing covers, of course, also additive manufacturing, other laser beam welding, other activities. Of course, today was on a bit ultrafast laser, the idea, but we really are providing also other applications for other kind of laser technologies and applications. So if it's not the case, you can still reach us offline. So maybe it was very clear. So the exercise went too good, Pablo. And then people don't ask anymore. Now, anyway, thanks a lot, Pablo, for this and the exercise. So I guess the people now will know a bit more what to do with us. And now we can maybe move forward and go to Paul. Finally, it's the turn to talk about tribology and how also some applications may be connected to the surface structure in a preparation of surfaces. So Paul, please. The floor and the attention of everybody goes to MTC.
Thank you very much, Francesca. Just bear with me while I open this up.
Yeah. So the share the screen is just the bottom green below. And you have to choose which thing you want to show us. Yes, something is coming. Yes, if you go to presentation mode.
Okay, just bear with me.
Mm-hmm.
That should now be in presentation mode.
It is perfect. There you go.
Good. Well, thanks, and nice meeting you all a little bit early on with my introduction. So you're aware of what we do at the MTC and some of the activities I've been involved with. But this has been a really interesting one. So we've been looking at laser textures for the cutting tool industry, the machining of various parts for a wide range of applications. To address the questions is not only how textures work in terms of their performance characteristics, but why they work as well. Why do textures actually work in specific applications? And this study was really done to address some of those questions for the specific application. So I'll just rattle through this very quickly, but the scope of or overview of my presentation looks at the back down to cutting tool modifications through laser texturing and then texture designs. We'll look at femtosecond laser processing and why femtosecond works really well for this application. And then we'll look at the assessment of the topographies produced, and then some of the testing that we do in turning tests, tribology tests, and tool wear analyses, and then we'll wrap up with some sort of takeaways from this presentation. So if we look at the tribology theory on the top right-hand side, if we look at the interaction between, say, two rigid surfaces separated by a hydraulic film, and under low sliding velocities, generally and higher contact forces or pressures, we have a boundary condition formed where we have metal to metal into reaction, if in the case of metal surfaces. As the sliding velocity increases, we have some separation into a mixed lubrication regime, and then full separation into hydrodynamic. And the sweet spot in the study of tribology is always this electro-hydrodynamic lubrication, where we have the lowest coefficient of friction in relation to, say, speed or viscosity or load. So kind of that's really where we're looking for. Now, in tool applications, where we look at the texture of the surface of a tool and the interaction, say, for example, with the chip or the workpiece material, in the presence of a coolant, we have all three of these regimes existing at any one time due to the pressure variation across the tool. What we're trying to do with texturing is bring the hydrodynamic regime closer to the cutting edge, which will increase cooling effect in machining, allow increased machining parameters, machining rates to be achieved, and also, of course, have the effect of reducing wear of the tool. So that's kind of what the objectives of the study were. Now, in order to achieve that, we've designed a whole sequence of experiments. We've done cutting tests. We've done the selection of 20-odd textures from dimples and grooves. We then use those input parameters for the actual tribo test setups as well, because we want to simulate those conditions closely. And we've allowed the laboratory-based testing then to be carried out to get a better understanding with the production of results. To have a summary of the scope of the features that we produced, 20 in each case. So we saw a little bit of this earlier, but this is specific to the sintered carbide cutting tool materials, which are a really common material. With ultra-short-pulsed processing, although the enthalpies of the ingredients of the material being a sintered material are quite different, by femtosecond processing, we can reduce the time frames of heat transfer and the evaporation of the material. So essentially, it's happening at the same time. It's not, of course, in real physics, but this produces very, very clean features with ultra-short-pulse processing. And we've seen this particularly with near IR wavelengths, and of course with the green wavelengths if you look at longer pulses. The parameters that we used for the processing are shown on the left-hand side, the bottom, and the scan strategies that we employed for dimples and groove textures are shown on the top left-hand side. Of course, a George Fisher machine was used for that, the one we have at the MTC. Now, after texturing, one of the critical criteria is the any evidence of recast layering, because looking at a friction type surface, we don't want corona effects or recast layer effects around the produced features. So the interaction between, or the relation between the untextured surface and the textured feature is absolutely critical. As are the dimensions and formations, the microgeometries, if you like, of the textures. So we look out for that, and with femtosecond processing, you can see in the sectional diagrams we see no evidence of recast layering, making it pretty much a perfect surface or surfaces for tribology. laser processing allows us to do this very quickly, as we've heard some of the other presentations early on this afternoon. Now, the first real machining test or mechanical test we've done is the machining test, which was a turning test where we capture the forces. Now, the force capture is critical because it allows us to then down select the various textures which are performing well. It gives us the input parameters for tribology testing and so on. So these are the captured the setup and also the captured forces in three components, three directions of force vectors. So once we've done the turning tests, we look at the change of cutting force in relation to an untextured surface. So the greater the minus percentage, if you like, is the greater the improvement. So this allowed us to select the best performing groove texture and the best performing dimple texture from the whole group of textures that we studied. It also allowed us to compute the average normal force to the in the machining operation, which we will then use for the friction test, as you'll see later on. So another interesting area is when we engage a cutting tool, we look at the area of engagement and the characteristics of engagement. Now, if you remember the Strybeck curve I was discussing earlier, where scarring forms into the boundary where high pressure exists, and intermediate into the mixed regime, and low pressure into the hydrodynamic regime. And we pick this up by gridding the surface and looking at the specific interreactions between the cutting tool and the workpiece. In this way, we were able to quantify both contact pressure in the different regimes and also contact areas. From that, of course, we can calculate pressure, and that's then how we have a starting point for the tribology testing. So those of you who are not familiar with a tribology testing arrangement, we have we've carried out the test on the Brookett UMT tribometer, where we have a reciprocating stage containing the cutting tool, and we have a counterpart material, which is the workpiece material that we were using in the turning test. And also from the determined pressures from the earlier study on turning, we could plot the range of experiments that we're going to do on the tribometer. The reason we use a lower pressure range is because we don't want boundary conditions, metal to metal. We want the mixed and hydrodynamic conditions, which are far more interesting, because EHL is that sweet spot which I referred to earlier. Now, if you remember the Strybeck curve, which I've put in here just for refresher memory, and the first plot of results, you can see the tops of the blue lines kind of follow the Strybeck behavior, which is really, really good news for us, because from that behavior plot, we can start to predict the characteristics of the textures. So once it follows a specific behavior, we can then predict. Incidentally, the coefficient of friction is captured from the center velocity of the oscillation. So that's shown on the top right hand. So what we thought we'd do is because the chip behavior on a tool is quite dynamic in the sense that it's different contact areas and different contact pressures, is to simulate some of those conditions in the tribo test, because the tribo test gives us a very high resolution of data which we can then analyze. So we applied a contact force of 10 newtons and varied the contact pin diameter from 2 millimeter to 1 millimeter to 0.5 millimeter, giving us the associated in the square function, the increase in pressure, which you saw earlier on my pressure curve. So from those, we could determine the EHL, the value. But more interestingly, as the pressure increased with the decrease in contact area, we saw a reduction in the coefficient of friction. And for 0.5 millimeter contact, a fairly flat part of the curve, and then EHL in the latter part of the curve as the frequency increased. Now, this is due primarily to the with a higher contact pressure to the boundary condition being formed, whereas the low contact pressure on the top left-hand side is more in the mixed and hydrodynamic. So we can start to say that textures work in different conditions in machining, and we can start to define those conditions in machining operations where textures actually start to work. In terms of the influence of entrainment area and at 12.7 megapascals effective pressure. And you can see the takeaway points from this is that for the dimple texture, the coefficient of friction through area reduction increased by 4.1 times. But on the open groove textures, the coefficient of friction reduced by 30.6 times. So it's a really big difference between different texture designs. So yeah, it really shows that the design of texture is really critical for cutting tool applications, whereas and really relating to the area of entrainment, where the open groove, of course, if you imagine your motor car tire with open grooves, it allows fluid to flow, where closed dimples contains the fluid, creating a far more hydrodynamic surface, and therefore the reduction or lower reduction in the change of coefficient of friction in relation to the entrainment area. Okay, the next slide, please. So the last part of the study really was on wear. So we've got the textures now. We say, oh, they're wonderful in performance. What about the wear of the tool? So the center panel shows you an unused tool, a dimple texture tool, and the groove texture tool, like we tested just early on the Tribo test. And after 9,426 meters of machining, so that's a fair amount of machining, the wear surfaces of an untextured tool versus the textured tool, and you can see immediately, oh wow, the textures are working. We can see that the low buildup of surface contamination and debris are far reduced with the surface textures that we down selected from the machining trials, and also and more critically, these wear scarring, which is formed by metal to metal, the boundary conditions are far reduced on the textured surface, or the two textured surfaces compared to the untextured surface. So with this buildup of evidence to show that how and why textures are working in the machining environment, it gives us a really good idea with regard to the application of laser produced textures. So the next slide, please. So yeah, that was a study, and as I was alluding to earlier, the takeaways from this, as we've just heard, that the texture surfaces would lower the surface, lower the coefficient of friction between surfaces significantly in relation to untextured surfaces. The dimple texture exhibited a far lower change to coefficient of friction than the open groove type textures, and we've seen in the wear results that the textured surfaces performed far better in terms of surface contamination and wear cycles, even after a long duration of contact. So thanks for that, and thanks for jumping in, Francesca, to the rescue. Nothing I could do with the frozen computer, so I guess that's it, and keen to hear about any questions maybe.
Thanks a lot, Paul. Actually, is my master of hosting. Sharara was sharing the screen, so we were offline trying to find the presentation again, but it went pretty fine. This is why we try to get them. So
good teamwork. Good teamwork.
You never can expect what the technology can do. Yeah. So Paul, thanks a lot for the talk. So we get to the end. If I don't see questions, are you sure? Nothing that can interest you? Ah, no, we have a question. So Hamid, please, you can ask the question yourself.
Unmute.
Yes, now we hear you.
Yes, okay. Hello, my name is Hamid Kalaycıoğlu. I'm a Chief Scientific Officer at Lumos Laser.
Ah, okay.
It's actually partner in the Pulsate project.
Very good.
And I would like to ask you about this absence of recast layers in the laser processing. Did you do any additional, did you use any additional methodology to prevent recasting during laser processing?
There was a fair amount of process pre-optimization. So normally what we do is we look at the generation of features, the typical features that we're going to incorporate into a pattern in scan lines or individual features, but by looking at process parameters and scan strategies to achieve that. So there's a fair amount of pre-work to be able to optimize what we're about to produce in terms of those the energetic, kinematic, and then the scanning strategies. So yeah, once we've got there, we incorporate that into patterns. But we don't do any substructural analyses. I've done substructural analyses using focus ion beam work and TM studies, but normally in terms of this development, we don't go that far. Just looking at them geometrically, first of all, on a high resolution 3D profilometer, and then also looking at and capturing high resolution images using scanning electron microscopy.
Yeah. Okay. So it's patented work, basically.
yeah. I think the nice thing is that once we achieve the optimum parameter sets, scan strategies for a particular material, like we were hearing for earlier, once we've got a family of materials, it doesn't really change. So we've got for sort of upscaling into a bigger study or into a sort of production process, becomes a lot easier because those parameters seem reasonably robust in laser processing, which is good news for all of us. I think once identified the particular laser, the material group, and then the parameter sets to operate, we find the laser process quite stable in fact.
Do you use assist gas or water splashing? I don't know, whatever you say. For example, additionally to laser scanning during these processes to prevent recasting?
We don't need to in this particular case. We of course the George Fisher machine that we're using uses 270 femtosecond. I remember that order from their laser source. So we find with that particular setup, we don't need to. It's a dual source, so when we switch to nanosecond, for sure we get a recast, and therefore the issues and needing some post-processing to eliminate the precast with longer pulse durations. But with our setup, it's as processed, so it makes it a lot easier for us, I guess.
So it's basically scanning optimization.
Yes.
That's
a very important part. Yeah, if I had to show you all the pre-experiments, you'll see a lot of issues in relation to the quality of the produced features and also some recast maybe creeping in. But one of the areas which we did find, and also part of some pre-optimization, particularly with sintered materials, is not precast in as much as the outgassing of the metallic phases. So we have tiny micro holes being formed in the structure, which are detrimental. Really, it's detrimental for the strength, not so much tribologically, but yeah, sometimes we see those issues, and by optimization we can reduce, if not eliminate them. We've done studies where we've had these features and we can actually remove them by optimized process parameters as well.
Thank you, Paul. For
okay, my pleasure. Yeah.
Explanation. Thank you.
Thanks a lot. Thanks a lot, Amit, also for asking the questions.
Right.
And so I guess I would say we talked really a lot. There was also some technical issue that a bit we lost some time, but not too much, because most of the time we were really like either listening to our speakers or really talking to them and asking questions. And we are already like beyond the buffer time I was planning. But if we have a final remark, a final questions, now is the time to shoot. Also from you end users that I see, you are here. And in any case, please keep in mind, these are all people here that would like then to keep in touch with you. So if there is anybody that wants to deepen some topic also offline, you are pleased and welcome to contact me or to contact all the two initiatives you saw. Maybe you will see the recording. You can maybe take all some social media, some web page if you didn't find us yet. Otherwise, we are very open to your messages, and we will connect you also with the speakers and the people here in the room. That's what also EPIC is doing, to a bit connect the community, the end user, the integrators to who provides the technology. And if you need help, of course, I mean, LAMPAS is about to come with the full machine. So stay tuned on that. And Pulsate is really ongoing in giving you opportunities to profit from the knowledge of our competence centers and our technology, covering the full spectrum of laser technology. So if you're interested, that's really ongoing. And we are really happy to welcome your request. So if there are no other questions, I would say I really thank you all again, all the speakers, all the participants, also all of you who ask questions and are interested in our activities. And this is not the last one, so especially we will go on with also combined webinars with the different European initiatives and with EPIC companies, because it's we see it's really nurturing the synergies is really effective. So I thank you all again, and I wish you a nice evening. And for all of you watching offline, I wish you a nice rest of the day when you are watching us. So thanks a lot, and bye-bye.
Bye.
Thanks, Charles.